Hi, my name is Meenakshi Sundaram and I am an application engineer working for Cypress Semiconductor at Chennai, India. I am going to show you a motor control demo using the third generation Cypress Programmable System on a Chip or PSoC. This PSoC has a 8051 microcontroller and programmable digital and analog blocks to create an entire system. The demo uses the development kit called the PSoC DVK. To know more about PSoC and the DVK, please visit our website at www.cypress.com. The motor which is being driven in this demo is an 8-pole 26-watt BLDC motor. The algorithm we have implemented can drive any permanent magnet synchronous motor or PMSM for short, or a brushless direct current motor or BLDC for short. The only modification required is to have the appropriate driver board that can support the wattage rating of the motor and an appropriate two-phase current measurement circuit to measure the maximum current consumed by the motor. The demo uses field-oriented control or vector control. I will refer this as FOC. FOC is one of the methods used in variable frequency drives or variable speed drives to control the torque and thus finally the speed of three-phase AC electric motors by controlling the current fed to the machine. The major advantage of FOC over other methods is that the rotor is monitored at every position and the algorithm ensures that the rotor magnetic field and stator magnetic field are always aligned at 90 degrees to each other. As a result, the torque or the tangential force is at its maximum. In order to achieve this, the precise real-time position information of the rotor is needed. This demo does not use any sensors to measure the speed of the rotor, but calculates it from the number of zero crossings of the estimated back EMF from motor phase currents and phase voltages. The position of the rotor is calculated by accumulating the speed over a period of time. Hence, this demo shows sensorless FOC. A single FOC loop, including current measurement, speed update, back EMF estimation, and the PWM generation, takes about 200 microseconds. For more details on timing, please refer to the application note that will be released soon. Okay, now let's move on with the demonstration. To begin with, the potentiometer controlling the speed is brought down to zero position. Then the motor is started by pressing the start-stop switch in the DVK. The potentiometer is then raised slowly till the motor picks up enough torque to start rotating. Yeah. And just raising it slowly. Now you can see the motor rotating. For more lively info of what is going on, PWM duty cycle of one of the phases is tapped out and displayed in the oscilloscope. You can notice how the frequency of the waveform and thus the speed of the motor varies with the potentiometer input, which I am changing. The frequency of the waveform is the electrical hertz or frequency of the motor, which is nothing but the rate at which the stator coils are commutated. The speed of the motor is 1/4 of that frequency because of the presence of 4 pole pairs in the motor being driven. So you can see how the speed changes with the potentiometer change as well as the electrical frequency in the oscilloscope. So that's it. Let me bring down the speed. Yeah. The speed is almost to zero. And then just stop it. That's it. So that wraps up the demo. Thank you for watching.